The most tricky part about this one is actually here, as I emphasized a couple of times. This is non-trivial. If there is no specific rule about this neighboring thing, and this is actually lattice, represent the lattice or network in our language structure. So this is the most complicated part, in fact, among these interaction terms. If we can assume that you can imagine some hypothetical situation where if this lattice structure is so regular, you may anticipate some simpler behavior. I mean, even in this non-zero J case. Because all of this simple calculation was possible because of this very simple form of this H term. So even for this J term, you may expect that there can be some kind of simplification as a result of this. Even when we talk about this very regular or mathematically simple lattice structure. And that's actually the case. That's exactly the case where for the one-dimensional structure. And we will deeply go into that part. And usually, when we talk about this non-zero J case, the most important or the simplest case would be, of course, we can actually set this external field as 0. Then it means that there's no external field. So you may assume that without the external field, there is no in this case, spin up and spin down is completely symmetric. It's actually called as up-down symmetry. So you think that there cannot be any preferable direction, and which is true. And of course, if you take average of this configuration, even without any calculation, you may expect that the real average magnetization should be 0. And that's kind of actually true, but this fact, the average magnetization vanishes, can occur in a very different way. For example, suppose you have this kind of random configuration every time, very disordered state every time. Then you will have this average magnetization would be 0, or at least very similar to 0. It's the random configuration, completely random configuration. And this is very similar to t goes to infinity for paramagnetism. Or H become, in fact, you have to specify that H over K with T goes to 0. But there can be other possibilities in this case. For example, as an extreme case, suppose you have 50% chance of all spin up state and 50% chance of all spin down state. So even in this case, you can just if you just simply take average of these cases, you will have exactly 0 magnetization. So these two situations, this situation and this situation, is clearly different because this represents the so-called disordered system, or where the entropy is maximized. So this is a disordered state. But in this case, even if the average magnetization is 0, you have either all spin up or all spin down state. So it is actually ordered state. But because of this intrinsic uptown symmetry, if you just take average without considering each of these configuration, you will get the same, the vanishing average magnetization. So you have to be carefully differentiate between this one and this one. So there can be some different way to distinguish these two. So this ordered state or spontaneous magnetization. This is spontaneous, even if the external field is 0, the spin themselves align to each other so that they can have this magnetized one. One practical thing we can try is that if you actually measure as I suggested, if we measure this absolute value of this thing instead of this just taking average, the absolute value of this one is 1 for every spin configuration, because there are just 2 configurations. But in this case, even the average magnetization for each configuration would be similar to 0. It's certainly not exactly 0, but it can have some kind of random fluctuation, but still it's quite different from this case. So it's a practical tip for the numerical simulation. For this case, the paramagnetic system, we only have basically the real interaction is occurring independently for each spin and the external field. And there is no correlation between individual spin at all. So somehow you can, for each spin variable, all of the other environment can be considered as so this Si. So you can consider all of the other environmental spins as Sj, as a single spin variable. And this treatment is actually exact for the paramagnetic system because there's no interaction between these Sj spins. So you can treat all of the other part of the system as a single thing, which is actually correspond to the external field in the paramagnetism. But for the real Ising model, this Sj is in fact composed of lots of different spins. So even if you want to treat this Sj as some representative spin, because of this large fluctuation among the other spins, there must be some kind of error the deviating from this behavior. So what they're trying to say is one easy way to solve this Ising model is that treating all of these other spin variable as a single average spin variable. Again, which is exact for the paramagnetism. But for real Ising model, even if you want to treat this all of other spin as a single object, because that is not absolutely true, there are some deviation from this average behavior. So we'll just, so better to use the analogy. So you have this spin variable, and you have spin 1, spin 2, and spin 3. If you take average of this, let's say, it's the up spin, two up spins and one spin down. So you want to treat this as a third spin. And one easy way to deal with solve this problem is just considering this plus one spin, this plus 1/3 spin. Of course, because of this fluctuation away from this average value, of course, you cannot just replace this problem with this problem. What I just described here, treating all of these other spin as a single average value, is actually called as mean field treatment, because replacing because the terminology comes from the setting that taking all of these complicated spin configuration with a single average field like object. So it's called mean field treatment. And we will learn about this in detail later as well. Approximation. As you can see, in the case of paramagnetism, you don't need to care about this at all. You just deal with the real single object called the external field. So this so-called mean field approximation is not really approximation. It's the exact treatment for the paramagnetism. Basically, what we have to do is a seemingly simple task of calculating the partition, of course. And partition function is, of course, sum over all the Boltzmann vector. So far, very similar to the non-interacting spin or paramagnetism. So here, beta j, and here I plus 1, because this is a one-dimensional structure, and plus beta h, and the same one. So you may get the impression that now both of these summation is a single summation, at least, even if there's some kind of nonlinear term here. Because this is a single summation, maybe it's better to solve this complicated form of this part. Imagine doing some two-dimensional system case, two-dimensional Ising model here. Then this term become much more complicated. It's not just I plus 1, but you have to consider above and below, and yeah. Maybe you think that's straightforwardly extended, but it's not. It's really not. Believe me. So yeah. So we have to solve this one, and for some reason that will be useful later, let's write down this. This part actually, like this. You may find it really strange now. Yeah. Yeah, I'm sure you are wondering what are you doing now, because you I just turned this simple term even more complicated part. Let's see if this is actually true. So of course, this one is the same one, but this is extra one, but index is shifted by one. But it doesn't really matter. As I already mentioned, we assign n plus 1 become 1 and n plus 2 become 2. It's periodically assigned. So it doesn't really matter. It's a sum over Si or sum of Si plus 1. And because this will add the same thing twice, we divide this whole summation by 2. The only reason why I make this simple term even more complicated term, make this simple term to this more complicated term is that somehow I just converted this the whole summand as a product of these two and sum of these two. This is actually important when dealing with some matrix formulation later. So let's start from this. So let's write down this explicitly. So it's basically exponential of beta j s1 s2 plus this one s1 times plus s2. This is the summation of all. So what I actually did is writing down this part as beta sum over n plus basically this. And because the summation is inside the exponential, so we can just split all the exponential for this indices. So this one and times exponential beta j s2 s3 s2 plus s3 times etc. And the final term would be sn s1 sn plus s. Again, you now feel that just make this problem very complicated. But let's focus on each of these terms, like this term. So this term, in general, we can treat this as a exponential of beta j si plus 1 plus beta si plus I plus 1. So of si and si plus 1, and this is sum of si and sj plus 1 actually. I think I have to read this one as well. So I have two typos, so I have to update it. And because this si can be plus 1 or minus 1, and si plus 1 can also be plus 1 or minus 1. So there are 4 combinations. So we can define this Si plus 1 as this matrix form. So this T matrix has 2 elements, Si and Si plus 1, and its matrix element is this exponential factor. So in other words, this T matrix sometimes is composed of T plus 1 plus 1, T plus 1 minus 1, T minus 1 plus 1, T minus 1 minus 1. And what is this? So this represents the S. So what's the element T when Si and Si plus 1 both are plus 1? Then we have to plug it 1, 1, 1, 1. Then the factor here is the exponential of beta j plus beta h. It's 2, so it's beta h. What about this? In this case, we have the product is now negative, and because this sign is different, the summation term becomes 0. So just this one. And in the same way, we can calculate this matrix form. In this case, if both spins have negative value, then this product is positive, but this summation is negative. So we have this one. So in this case, we can write down this partition function as T S2 S3, T S3 S4, etc., and T Sn minus 1 Ts, and Tsn and Ts1. Yeah. Because this matrix element is just this formula. So it's a product of this matrix element, the very long product of this matrix element. Then now let's explicitly write down this. By the way, this matrix is called the transfer matrix, representing the relationship between the two adjacent spins, which will be used a lot for various part of the statistical physics. So it's better for you to be familiar with this spin. Then let's explicitly write down this as S1 plus 1 or minus 1, and S2 is also plus 1 or minus 1. Plus 1. And this, all the products like this. Perhaps you feel that now it's become more puzzling and puzzling. But let's just take this example. Let's first rearrange all the summation of here, and then put this even index here, and etc. By assuming that Sn is a even number. It doesn't really matter, but let's just for the notational convenience, let's assume this. So it's a odd and even index. this formula may not look familiar to you, but actually, if you calculate this matrix product, it's A11 B11 times A12 times B21, etc. So the elements, if you assume this as a C matrix, then element of C11 is actually sum of A1I times BI1, and I is 1, 2, 2. So in fact, this particular formula is actually the product of S1, S3, the square of this S1. You can just replace this B matrix as the same as the A1, then we have this one. Or let's just explicitly write down. The matrix elements of square of the matrix is actually the A I K and A K J and sum over K. This is a simple matrix product. So eventually, by using this formula, all the even indices will disappear and leave this square part. So it will essentially be S1 plus minus 1, S3 plus minus 1, etc., and Sm minus 1, and S1, S3 squared, and S2, S4 squared. Oh, it's not true. S3, S5 squared, and Tsn minus 1, Ts1 squared. Yeah. But we can use this identity again to generate Ts1, Ts5 now to the fourth. So if you eliminate all the summation term like this, you will end up with this S. Only remaining term is Si1 and Tsi and Psi and to the power of n. You can verify it yourself. So relatively, well, it's not quite straightforward, but if you follow this carefully, you can prove it. Then what is this? So this is the sum of all the the diagonal elements of this matrix element. Suppose you have a matrix and with the elements ij, then this corresponds to, for example, if A has this matrix form A11, A12, and A2. This formula means that sum of all the diagonal elements, this one. sum of diagonal element of the matrix. It's not as famous as a determinant, but it's called trace. Yeah. It may appear in quantum mechanics. Yeah. So basically, this is a trace. So sometimes we denote it as a trace or transfer matrix of the nth product of the trace matrix. So all we need to do is just this huge problem of the one-dimensional Ising model is just and the going down to this multiplying this T matrix n times and getting trace, which is of course possible, but it's really tedious. Of course, it's possible if n is like a 2 or 3 or something. It's really hard. So we will use some clever mathematical identity developed in linear algebra. In linear algebra, for real symmetric 2 by 2 matrix, there exists a unitary 2 by 2 matrix U such that U inverse, which is the same as U transpose in fact, but times T times U will become diagonal matrix. And what is this lambda? Yeah. These are eigenvalues. So this should be done. This should be possible for any matrix where in general, let's suppose let's order this eigenvalue as this. So these are the real eigenvalues of the transport matrix T. So this is what we called matrix diagonalization by unitary transport. And there is a very famous known fact about linear algebra is that trace of T is the same as the sum of eigenvalue. Instead of actually doing the product of these n times, we can just diagonalize this matrix. Trace of this T to the power of n would be the same as this one because, as I mentioned, these are just the identity matrix. So we can put this U and U inverse between all the T product. But this is a diagonal matrix. So if you multiply this diagonal matrix by itself, of course, we will have this one. Diagonal matrix is just the numbers, basically. Since we don't really need to care about this off-diagonal element. So basically, nth power of this diagonal matrix is just element-wise nth power. So the trace of this matrix would be, of course, sum of eigenvalues or some of the diagonal elements. So here, the trace of this matrix would be the same as the nth power of eigenvalue of this matrix. So the only thing remains is that calculating the eigenvalue of this matrix and taking nth power and summing over this. The book kindly introduce how to calculate the eigenvalue by setting this determinant. So you can, since this is a 2x2 matrix, you have this quadratic equation. And according to the formula you learn in middle school, you have this solution. And this is a solution. So rather complicated form. Now you have this solution. Because of this argument, now the whole process of calculating the partition function become, and since the eigenvalues are here, this may look very complicated, but luckily we will be interested in h goes to 0 limit. So in this case, this one becomes 0 and this one becomes 0, so it will be disappear and this become 1. So lambda plus here become exponential beta j. So let's assume this limit, and this one become 1 plus minus, this one become plus square root of exponential this one. But this is plus, this is a square of exponential minus 2 beta j. So this will become this one. So, and again the formula form, twice the hyperbolic cosine of this one. And what about this? The same, but minus. So it will eventually twice the hyperbolic sine of beta j. So this cosine hyperbolic factor and sine hyperbolic factor become two the larger and smaller eigenvalues in this case. So it will become twice cosine hyperbolic beta j to the nth power and this one. And then for the given temperature without external field, so twice hyperbolic cosine beta j here and 1 plus hyperbolic tangent and to the nth power this one. And we will actually taking another limit where this tangent hyperbolic is always smaller than 1. So as n goes to infinity, we can approximate this partition function as this, the simplest part. Yeah. So again, it's almost the same as the non-interacting spin system. But instead of h, we have j now. Yeah. So we have this free energy minus kBT log C. And again, this is minus kBT log this one. But also using this thing, let's plug in this one. But now for the completeness, we actually re-plug this possibility of the non-zero H as well. Then we can have this form in KBT. This rather complicated formula because we kind of revive this H term. Pretty complicated looking term, but the shape is very similar to the one we already familiar with for the non-interacting spin term. So again, except for this particular singular point, so analytic everywhere, except for this critical point where both variable become zero, right? This cusp point. The formula is really similar to the non-interacting spin. So we have all this derivation for the free energy and average magnetization like this. But now we have a H term. So it's a little bit more complicated than before. We have both J and H term now. But these are all just algebra. And for when J becomes zero, of course, we will rediscover this tangent hyperbolic thing. And for H goes to zero, we will have this zero magnetization for any finite temperature. So meaning that without any external field, it's not possible to have a spontaneous magnetization for the one-dimensional case, at least for any finite temperature larger than zero. But for temperature becomes zero, which is actually a singular point, then we can have a +1 or -1, but this is a very special case. There's no finite temperature phase transition is occurring here.